Alright, how's it going, AS Chem? This is a video for your Unit 5 Celebration of Learning study guide, where I'll be walking through some problems for you guys, showing you guys how to do it, and helping you just be more prepared for your celebration of learning. One thing to note before we get started is that for the celebration, you will have the following tools. You will have the chart of the molecular geometries. You will also have, as always, a periodic table, as well as an electronegativity chart. It is your responsibility to know how to use these tools, of course, but they are there for your disposal in order to help you answer the questions, and I'll be using them throughout this video. And so let's start off with number 1. This goes back to 5.1. Now, do note, though, this is our Unit 5 at Celebration of Learning. Most of it is going to be mostly 5.3 to 5.8. There will be a little bit on 5.1 and not really that much on 5.2. It's the things that are on here, and especially we're starting off with number 1, right? Ionic, metallic, or covalent. Remember, we did that lab, You Light Up My Life, where we saw that there's kind of 3 categories, 3 kind of classes of compounds. We had ionic, metallic, and covalent. And so what we're doing here is we're applying that knowledge again to determine between these what are ionic, metallic, and covalent. And that's really the only thing that's from 5.1 to 5.2. Yeah, once we get to number 2 on, it's really just 5.3 and on. So do know how to do this, but otherwise don't really spend too much time on your 5.1 and 5.2 notes. It's going to be mostly 5.3 to 5.8. So let's do number 1. For number 1, ionic, metallic, or covalent. Sorry, this actually got done twice. This shouldn't be A. But anyways, we're looking at NaCl. Now remember that if we're just looking at the formula, that an ionic compound is going to be a metal plus a non-metal. A covalent compound is going to be a non-metal with a non-metal, and a metallic compound is going to be a metal and a metal. And so here, if we look at NaCl, what we have to do is take a look at the periodic table, find Na, and remind ourselves that everything on this side of that staircase is going to be a metal, and everything on the right is going to be a non-metal. And so what we see is Na is a metal, Cl is a non-metal, so we have metal, non-metal. This must be ionic. NH3 is N is a non-metal, and H, remember, that's the only one that's on this side, but is also non-metal. So we have 2 non-metals, so therefore we must be covalent. Right? So this is covalent. FeCu, we have Fe here, and we have Cu, so therefore what must this be? This must be, right, 2 metals, this is metallic. All right, CH4, we have non-metal and non-metal, and so this is going to be covalent. H2O, H is a non-metal, O is a non-metal, and I'm not going to pull out the periodic table again because I think you've seen it enough. It's going to be covalent, therefore. This is a metal, this is a non-metal, so therefore it's ionic. And so that's how you do the formula ones, right? You just have to figure out, okay, for each of my atoms, is it a metal or a non-metal? And therefore, if you know this, then you can just apply it. All right, now let's take a look at these, where these are telling us a little bit about the kind of properties of the compounds. And this really goes back to the lab, right? Remember, so we had 3 compounds, or 3 categories of compounds, 3 boxes, if you will. And the first box was things like salt, NaCl. Okay, so I want you to remember NaCl, right? That is ionic, right? And salt, we know at first it doesn't conduct electricity. But then if you put salt in water, right? If you put salt in water, it is going to dissolve, right? We know that salt dissolves in water, and it also does conduct electricity. One way that you can know this, remember this, is remember salt and the such NaCl, and also things like potassium ions are electrolytes, right? In your Gatorade, in your sports drinks, you have all these salts that are electrolytes, and what that means is that they allow for electricity to be kind of conducting through the body. A little bit of an oversimplification, but yeah, they conduct electricity, electrical charge. And so NaCl also does conduct electricity when dissolved in water. And so if you remember these things, about NaCl, you can remember the ionics and their kind of properties. And so things like this, things like NaCl, matches up with this description. A vial that contains a brittle crushed solid at room temperature, right? So it's kind of powdery. It doesn't conduct electricity at first, but it does dissolve in water. And when it dissolves, it does conduct electricity. That's things like salt, which is ionic. And so if you remember NaCl, you don't have to remember a bunch of ionics, but please remember NaCl is ionic, and then you can gain a lot of information from that. Cool, okay. The second one is things that sometimes conduct, sometimes don't. And so remember, the things that are sometimes doing something and sometimes don't, those are always going to be covalent. And we know the reason for that now. The reason for that is because we have two types of covalence. We have polar, which are charged, and non-polar, which are not charged. And so obviously those are going to have very different properties. Polar is going to be able to conduct, but non-polar isn't. And so that's why we have a sometimes do, sometimes don't with covalence. Okay, so anytime you see sometimes, that's going to be covalent. It's a covalent compound. Cool. And then lastly, if you can have an example for the metals, right, I want you to think of copper, right? Copper wire, which we used in this lab, right? Of course, that does conduct electricity immediately. Sorry, so this is a metal, right? Copper is obviously a metal. It does conduct electricity, but it doesn't dissolve in water, right? And so if you remember the properties of copper, you can remember the properties of metals. And so something that's malleable, right? It's solid but bendable, right? Yeah, that's copper. It's a solid at room temperature. That's also true of copper. And it conducts electricity, but it doesn't dissolve in water again. Yeah, right? That's all copper. And so we know that this is going to be a metal because it's just like copper. So if you remember copper as your quintessential example of a metal, you're going to be able to match things up. Cool. Okay, so moving forward, right, we see here this kind of cube-like structure. Remember, we call this a lattice, right, and that belongs to the ionic compounds. And so anytime you see a cube, a lattice structure, we know we have an ionic compound. Here we have Cl and Cl. Those are two non-metals, and so we know that this is going to be covalent, right, but also we can see here that these are sharing. And sharing, right, is also referring to covalent, and so we know all the more that this is covalent. Cool. So continuing on, here we see a sea of electrons, and remember the sea of electrons is for metals, both of whom, all of whom want to dump their electrons, and so therefore they are dumping it and creating a sea, and so this is metallic. Cool. So going on, let's do some of these. So give the name, and I give you a hint. First, determine if the compound is covalent or ionic. Remember, we have different rules for covalent versus ionic compounds. And so, yeah, the first step is going to be to determine if it's covalent or ionic. And remember, the big difference here in the rules is going to be in their prefixes. Remember, if you remember NaCl as your quintessential ionic, we know that NaCl, what's its name? You know, a lot of us already know, we've had that memorized for years as kids, is sodium chloride. NaCl is sodium chloride. Do you see any prefixes here? Right? Do you see a mono or a di or a mono here? Right? No, we don't, right? And that's because for ionics, there are no prefixes. Versus, if you kind of keep in mind for covalence, if you think of H2O, remember that was the dihydrogen monoxide, DHMO, kind of prank, right? And so I did that for you guys because, yeah, hilarious, I know, but also just because it reminds us that we need to have prefixes for covalent compounds, right? And so prefixes are necessary for covalent compounds. And so we can use that idea here. If we see NaCl, we know, right, it's ionic. All right, let me also make that for people just looking at the key, right? And so something like NaCl, which is ionic, is not going to have prefixes, so we just take the sodium, Na, and then the chlorine. Remember, we turn it to chloride. All of these are going to turn into ide endings, and there you have it. And so it's going to be sodium chloride. Now, magnesium is a metal. Bromine is a non-metal. And so again, we have an ionic compound, and so no prefixes, just magnesium, and then the bromine becomes bromide. Nice, cool. CO2, now CO is a non-metal, and O is also a non-metal, so therefore do we need prefixes? Yes, we do, right? We're in a situation of covalence, and so prefixes are needed. C is carbon, O is oxygen, it's going to become oxide, and then it's 2, so it's going to be dioxide. Nice. All right, CH4, C is a non-metal, H is also a non-metal, so we need prefixes. This is going to be carbon, 4, tetra, right? Remember, so you need to have your prefixes memorized. And then H is hydride. Yeah, so do note that, right? Prefixes do need to be memorized. That's not something you're going to be given on the celebration, so you need to have that memorized. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Remember, take a look at our slides if you need to, but yeah, have those memorized. Cool. Okay, so PCl5, right? That's again a nonmetal with a nonmetal, and so we're going to have phosphorus, penta for 5, chloride. Cool. Okay, so I'm gonna kind of leave it off there. Now, also, I do notice and recognize that, for example, I put Cu in here, and some of you guys are gonna say, we don't know Cu, and that's true. I mean, at this point, hopefully you guys know there's copper, but I will have us have more, probably up to 35 at least memorized by next celebration. But for now, if I put something like Cu on the celebration, I'll give it to you. But hopefully you guys are just starting to remember it just by being exposed to it. So anyways, so let's go on. Hopefully you guys understand how to do this at this point, figure out if it's ionic or if it's covalent, and then that determines if you have prefixes or not, and then just name it. Cool. Okay, so which of these two has greater lattice energy, and why? Number 3. The key to these problems, remember, is Coulomb's law. Coulomb's law is what determines kind of how strongly attracted two charged compounds are together. And so if I can actually bring you the lattice to remind you, the lattice is this thing. All right, and so remember these were magnetic, and so what we could see is that, hey, yeah, that they're kind of stuck together. Now, how strongly they're going to be stuck together depends upon two things based on Coulomb's law. It's going to depend upon the distance between the atoms as well as the charge, right? The size of the charge. So +1 versus +2, etc. Now, distance isn't really a factor here. It is actually if you get into higher level chem, but that's, for now, we're just learning the basics. So charge is really what's going to be determined here. And so you say, well, NaCl, it doesn't have a charge. And you're right, overall it doesn't, but remember, when you have NaCl, you have Na+1 and Cl -1, right? Because remember, you know, to make them happy, right, you could draw all this out, and you could be like, well, remember, Na is going to give 1 to Cl, so then you're going to have Na+1, and Cl gained 1, so it became -1, right? And so that's how we form NaCl, right? +1, -1. You could do all that work to do it, but also you could just remember, hey, Na has 1 valence electron, right, based on its position, so it's going to want to give up 1 and become +1. Cl has 7, it's going to want to gain 1, and therefore become -1. So yeah, Na has a +1 charge, Cl has a -1, and they're attracting each other because of that. But Ca, with the 2 Cls, right, what we see here is Ca is going to have a +2 charge, and Cl again is going to have a -1. And so what we have here is kind of a +2 attracted to a -1. It doesn't matter the fact that there are 2, but a +2 and a -1 are going to attract more strongly than a +1 and a -1 because of the size of the charge, right? So CaCl2 will have the greater lattice energy because the size of its charge is larger. Cool. Okay. So, if we were to take Al and Al2O3, right, Al is going to have a +3, and O is going to have a -2, right, because Al has 3. Remember, 13, we take off the 1 for all these guys here. And so Al has 3. It's going to want to lose 3, not gain 5. Gain 5 will be too hard. It's going to just gain, or lose 3. So it's going to be a +3. O has 6. It's going to want to gain 2. And so +3 and -2. And then SrCl. SR is going to want to gain, or lose 2. So +2. Cl is -1 again. And so what we can see is always going to be this, again, because the size of this charge is larger. Cool. Okay, so moving forward, how many electron domains are on the central atom? Remember, 1 electron domain, right? 1 balloon. This was the balloon animals. Is going to be equal to either 1 lone pair, right? So that's when you have set of 2 electrons around an atom, or if you have one single bond, or one double bond, or one triple bond. And so this is what always confuses students. They think a triple bond is worth 3 domains or a double bond is worth 2. It's not. One electron domain is any one of these things, okay? So do note that. And so when we take a look here, we're like, okay, that's one domain, that's another domain. And remember, we're going around the central atom, okay? Another thing that sometimes students get confused by is they look at things like this. And it's like, yeah, sure, O is important, but not for, you know, shape, because we're only looking at the central atom, which is C here. And so we have 2 things around C, so we have 2 domains. Nice, okay. Again, taking a look at C here, the H's are around it. We have 1, 2, 3, 4 domains. And then around this C, again, this is the central, we have 1, 2 domains. Nice. Continuing on, here our central atom is nitrogen, and we have 1, remember a lone pair is 1 domain, 2, 3, 4. So 4 domains, okay? And so the reason I'm asking you this is because this is gonna help you, right, when we're doing this, when you're determining geometry, right? So it's just a little practice of geometry, like how many domains does it have? And so we're gonna be able to determine, we're gonna be able to use this chart better if we can figure out how many domains something has around it. And so, right, because this is the number of domains and this is the number of lone pairs. And so if you can take a look at something and determine its domains and lone pairs, you're gonna be able to figure out shape. So that's just a little practice there for you guys. Continuing on to number 5, fill out the following table. I should have wrote Lewis dot diagram here, I'm sorry. It's a typo, but yeah, Lewis dot diagram. So we're going to figure out for H2 the Lewis dot diagram is 3D shape / name, as well as if it's polar or non-polar. So starting off with H2, remember H is going to want to form 1 bond, right? Because it has 1, it wants to kind of gain 1. And so the nice thing is hydrogen, there's 2 of them, and this one wants to do the same thing, and so they're just going to form a bond like that. And so what we're going to have is we're going to have just something that's linear, right? Because if you have only 2 things, no matter what, it's going to be linear, right? Like think about it, if you have a dot with another dot, it doesn't matter where you place that second dot, right? Whether you place it here or, you know, if you place it, and let's erase that, right? So if you place it there, you have a line, but also if you place that dot here and connect the line, connect the dots, you still have a line, right? 2 dots connected are always going to be a line. It doesn't matter how you shape it, right? And so, yeah, it's going to be linear there. And so polar or non-polar, well, here's the thing. Are either of these 2 stronger? Do either of these 2 have a higher electronegativity? No, I mean, they're both hydrogen, right? And so the electronegativity difference here is 0. And that makes sense, right? Hydrogen has the same strength as hydrogen. There is no pull either way, and so this is non-polar. Right? There are no dipoles, let alone a net dipole. And so that's H2, and it's going to be linear. And then going off to F, remember F has 7. It wants to kind of form 1 bond, and the nice thing is if we have 2 Fs, they're just going to, right, have this kind of connection here, right, with F7. They're going to share this together. Okay, so this is their shared pair. 6 of their own, 2 shared, and so they both have 8. Nice. Cool. And then oxygen, we're going to have each of them want to form 2 bonds, right? So we can have 4 of its own and then 2 shared. And the nice thing is it has itself. And so, right, we can have here 4 of its own and 4 shared. And then again, also here, sorry, this was linear, this was also linear, and these were both non-polar, right? For the same reason as stated above. 2 points are always going to be linear, and if you have the same thing, it's going to be non-polar. Cool, okay, so, and then we can kind of cap it off with nitrogen, right? It's going to have 2 of its own. It's going to want to share 3. And so we're going to have something like this. Again, linear and non-polar. So remember, and this was kind of just to review for you guys, remember, things like fluorine are going to want to form 1 bond. Things like oxygen are going to want to form 2 bonds. And then things like nitrogen are going to want to form 3 bonds, right, in order to get their full valence shell, which is normally 8. But sometimes, for example, with hydrogen it's 2. I should really write sometimes. Or sometimes 2. Cool. Okay, so continuing on. We go on to H2O. And H2O, the way it looks is, okay, well, hydrogen wants to form one bond, oxygen wants to form two. So what we should do is we should have, looking like this, where it's going to want to form one bond each. The nice thing is hydrogens are here, and they're going to want to form one bond each as well. And so we get something like this. Now, of course, the geometry isn't correct, but we'll get to that. And so, actually, maybe I should draw it with the correct geometry, right? Because when we get here, when we're talking about 3D shape, oh, sorry, actually, yeah, we are doing 3D shape. But it's especially important, right, for polarity, because if you don't draw it the correct way, you're not going to be able to get the correct 3D shape. And so here, right, what's its shape going to be? Well, how many lone pairs do we have? We have 2 lone pairs and then 2 bonds, right? And so how many domains do we have total? Where each of these are a domain, and so we have 4 domains, 2 of which are lone pairs. And so 4 domains, which 2 of which are lone pairs, is going to be bent. And so we have a bench shape, and so we're going to draw it with a bench shape. And so there you have it. Now, is it polar, is it non-polar? Well, we take a look at our electronegativity chart, like H and O. That's a 1.24 difference. O minus H, right? 3.44 minus 2.22, sorry, 2.20. And so the difference in electronegativity is equal to 1.24. That is well above our threshold of 0.5. And so there are going to be pulls. Oxygen is going to be pulling towards itself. And so overall net, remember these two have kind of 2 components. There's this up, sorry, it's to the left and up, and this is to the right and up. The left and the right parts are going to cancel, but there is going to be a net pull of both of these guys kind of coming together. So that's our net dipole. And so there is a net dipole. That net dipole is going towards oxygen. It's up and towards oxygen. And so there's a net dipole, so it is polar. Nice. All right. So then going on to NH3. NH3, the way it looks like is we have 2. And then we're going to want to form 1 bond each. The nice thing is we have 3 hydrogens. So we can just do nice, nice, I'm sorry, and nice. And then everyone's happy, right? And so then the question is, what is the geometry? Well, let's see. We have 1, 2, 3, 4 lone pairs, or sorry, 4 domains, only one of which is a lone pair, right? And so look here, we have 4 domains, 1 lone pair. This should be a trigonal pyramid, right? So we can draw it as a trigonal pyramid. And so now we can see, okay, what is the polarity? Well, N and H have a 3.04 minus 2.22. Not a math guy, but I think that's 0.84. And so 0.84. So therefore nitrogen is pulling towards itself. And so, right, basically we're kind of like in this situation where if I could, I would just make this into a lone pair, right? So imagine this is a lone pair. We have these guys pulling in all different directions. Now this is pulling this way, this is pulling this way, this is pulling this way. Their directions cancel, but they're all pulling down, right? Do you see? These are all pulling down. So there is a pull. It's down. So the pull is, or sorry, not down. Sorry. Nitrogen is all pulling up, right? So it's going up this way, up this way, up this way. The directions cancel, but the overall pull is all going to be up. And so there is a net pull. It's all going up towards nitrogen. And so therefore, it's going to be polar. Nice. Okay, so I'll let you guys do these, but I'll put it on the answer key. But just for the sake of the video, so it doesn't go like an hour, let's just go on to number 6, and that's when we start getting into organic chemistry. Now, organic chemistry, one of the big things that we learned was the bond line drawings, right? And so something like this, it looks like a squiggle, but it's really not a squiggle, right? We said that each one of these little points we can put a circle on, and those are carbons. And so how many carbons do we have here? 1, 2, 3, 4. And so we have 4 carbons. Remember, meth, eth, prop, bute. And so therefore, this is bute something. Now, what specifically is it going to be? Do we have any double or triple bonds? All right, we don't see any double or triple bonds, right? So remember, that's going to be ane, right? So if we have only single bonds, it's going to be ane. If we have one double bond, okay, so it's not saying that we're going to have a bunch of double bonds. It's just saying, hey, one double bond is going to be in, and then one triple bond is going to be ein. Okay. And so, yeah, we're going to have butane here because we only have single bonds. And then the formula here, you could draw it out fully, right? So if we have 4 C's, the way to make everyone happy is we're going to put bonds so that all of them have 4, right? And then we're going to fill up those bonds with H's. And so then we just check to see, is everyone happy? Does this guy have 4 bonds? Yep. 4 bonds, yep. 4 bonds, yep. 4 bonds, yep. Right, so all 3 of these guys are happy, and so we have all of our carbons and all our hydrogens. So we have 4 carbons, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So there you have it. That's butane, and that's what this is. So continuing on. Okay, I'll go on to this one. Right, with this one we have 1, 2, 3, 4, 5 C's. So our 5 is going to be pent. But we see here a double bond. And so we know that if there's a double bond, it's going to be not pentane, but pentene. Then to determine the formula, we can say, okay, well, carbon, carbon, 1, 2, 3, 4, 5. We see there's a double bond here. And so as we're doing this, we see that we already have 2 bonds. So we can just put 2 lines around this guy. This has 1, 2, 3. So we can put a 4th there, 1, 2, 3, 4, 3, 4, 1, 2, 3, 4. Cool, and then we can put those hydrogens on. And there you go. So the formula here is going to be C5, H1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10. And so that's going to be pentene. Now, one other thing that we learned, though, is that not only is this going to be called pentene, but actually, to be even more detailed, and you should be this detailed on the celebration, is to say, okay, not only is this pentene, but the carbon double bond is actually occurring on the first carbon, right? So remember, we can number our carbons. You could go left to right or right to left. But yeah, this is going to be carbon number 1. And so this is not just pentene. We're going to say, hey, it occurs on carbon number 1, so we're going to call it 1-pentene. That is different than 2-pentene, which actually we can see here, right? Here we have 1, 2, 3, 4, 5 carbons again, right? So it's going to be pentene, but specifically we put the double bond on the second carbon, so it's going to be 2-pentene. So there you have it. And so you can see, right, how this is different, right? Having this here is different than having it here. And so there is this difference, and we describe it by putting the number by the number carbon that we're putting the double bond on. But the formula is still going to be the same. It's going to be C5H10. You could draw it out and prove it to yourself, but that is true. These are both pentenes, and so they have the same formula. Cool. Okay, going on to here, ethyne, right? Ethyne is kind of telling us there's going to be a triple bond, but then also, what does eth mean? Remember, okay, eth, that's 2 carbons. So we're like, okay. And sorry, actually, I apologize. I should have put this here, right? You guys could have drawn there, but my mistake. But yeah, so let's just draw it here. So we're going to have carbon triple bonded to another carbon, so 2 carbons. And then we have 1, 2, 3 bonds, 3 lines. So all we need is a 4th. So there you go. That's ethyne. Formula is going to be C2H2. Very nice. All right, going on to 1-butanol, right? Bute, meth, eth, prop, bute. That's going to be 4 carbons. The ol, remember that tells us that we have an alcohol attached. Now, where is that alcohol going to be attached? Well, it's on the first carbon. And so we're going to have here carbon, 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 carbon. So 4 carbons. And then on that first carbon, we're going to put, actually, let's maybe put it here. It doesn't really matter where on that first carbon you put it. But yeah, let's put that OH here. Cool. And then we're going to fill out the rest with hydrogens. Remember, that's what you always have to do in organic chemistry. Make the carbons happy, giving it 4 bonds. And those bonds are going to be hydrogens. Cool. Okay, so we have C4H9OH. Now, you could also do C4H10O. Generally, though, we kind of put the OH to the side so as to tell us that, hey, it's an ol. It's an alcohol. But again, you could have actually put them all together. Cool. Okay, so now we go on to 2-butanol. And so what that means is it's kind of similar. we're going to put 1, 2, 3, 4. And then on that second carbon, we're going to put an OH. And here we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And so there we go. Nice. Now the formula is still going to be the same. Again, you can prove it to yourself. You count all these, but C4H9OH. And then also, let me kind of just show you the bond line drawing for these, right? So for example, for this one, we have 1, 2, 3, 4 carbons. And then we're going to have an OH here attached to that last carbon. Versus here, we're going to have 1, 2, 3, 4 carbons. And then on that second carbon, we're going to have the OH. Okay, so we can see kind of the difference in the bond line drawing too. Cool, okay. So let's continue on. Let's go on to, let's maybe just go over the oic acids, right? So remember, the oic acids are going to be the carboxylic acids. So that's Cu, right? We're adding on a Cu to the end. And so butanoic, right, is going to mean we're going to have one meth at the but 4 carbons. And so we're going to have 1, 2, 3, 4. Remember, that's 4 carbons total, one of which at the end needs to have the Cu group. And so it's going to look like that, right? And then the rest of these we can just put hydrogens on. Nice, 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 nice. And again, note, if we wanted to, we could do it 1, 2, 3, 4. Drop like that as well, right? I'm just trying to put a line here to say that, maybe. I don't know if people with the key are going to understand what I did there. I will just leave it like that. Cool. Okay, so that's that one. All right, then we go on to this. Remember, anytime you have a closed thing, it's going to be cyclo. Now, how many do we have? It's going to be 1, 2, 3, 4, 5, 6. So this is cyclohex. There's no double bond, so it's just hexane. Okay, so cyclohexane. Now here we're adding on a chlorine group, and so we can call it cyclohexyl chloride. Okay, so cyclohexyl, we turn it into ul, and then chloride, for that chlorine that we added. Cool, okay, then going on to this, right, if we have 2 groups, now what we're going to have to do is we're going to have to number our carbons. Now, you could start here, or you could start here. Let's just start here. And so we're going to do 1, 2, 3, 4, 5, 6. Cool, okay, so on the first carbon, we've put on a methyl, and so we're going to say 1 methyl, 3 chloro, cyclohexane. Okay, because it is cyclohexane. And so once we start putting on multiple things, then we're just going to turn it into cyclohexane and just put all the things at the beginning before it. But if it's just like this, you could have technically called this chlorocyclohexane. But yeah, I think the kind of informal way we call it is cyclohexyl chloride. But I get it if you call it chlorocyclohexane to keep it consistent with this terminology. If we have more than one thing, we always put everything before. That probably makes more sense to do it that way. But also maybe I've just gotten used to it. But yeah, so that's how you do it. Well, let's keep going. Oh, these ones. Okay, what functional groups are present? Okay, so that's actually kind of easy. Just take a look at the study guide that I gave you and see, okay, what functional groups, what are the functional groups? And let's try to find them here. So here, right, take a look and we're like, oh, that's interesting, right? We have Esther, right, with her dog, right, remember? And so therefore here we have an ester group, right? So that's one. And then the other one, you see here, we're like, oh, hey, look at this, right? I remember, you either get it or you don't, right? Remember that chart? You either get it or you don't. And so this is not either, but ether. So this is an ether group. And then going on to these guys, well, this is kind of easy, but what is this thing here? It's Cu, right? We're adding on a Cu at the end of the methane, and so this is a carboxylic acid, right? Cool, okay. So again, I can't really explain too much on these, it's just more so like match it up with your, with the things on your organic chemistry study guide. Anyways, continuing on, what is the formula for the following molecules? Now, again, I was really, The reason I put this in is, again, because a lot of you guys are going to take AP Bio next year, and I want to make sure that you guys can take a look at some different things that you'll see and be able to see kind of the carbon and the bonds that are occurring here. So something like melatonin, the sleep hormone inside of your body, what's actually going on here? Well, remember, anytime we have like a little vertex like this, we really have a carbon attached to another carbon with another carbon and another carbon and another carbon and another carbon. Now do note that each of these carbons need to have 4 bonds, and so if they don't, we're gonna add on hydrogens. So here we have 1, 2, 3, 4, so it's good. 1, 2, 3, 4 is gonna be the hydrogen. 1, 2, 3, 4, good. 2, 3, 4, good. 1, 2, 3, 4, 1, 2, 3, 4. All right, continuing on, we got 1, 2, 3, 4, 1, 2, 3, 4. All right, then this nitrogen here has 1, 2, 3. That hydrogen is attached to it, so it has all it needs. Cool. Okay, continuing on, we have carbon. 1, 2, 3, 4. Carbon here with 2 hydrogens. Cool. Here, this nitrogen has 2, 3 bonds. Carbon. 1, 2, 3, 4. Okay, so that is good. So now let's just count up what we have. We have carbon, hydrogen, oxygen, and nitrogen, and generally we're going to go left to right, meaning carbon is going to come first, and then actually I guess I'll probably put nitrogen first and then oxygen. For some reason though, we go left to right, we always put carbon and then hydrogen. Again, some of these things are just kind of conventional things, meaning, for example, like, well, why do we have stem changing verbs in Spanish? It just sounds right. You know what I'm saying? Now that's annoying for a kid to hear, but that's just how we do it. But you'll get used to it eventually. But all that to say, I get that it's like, okay, why do we do it this way? If you mix up the order, that's fine. But yeah, this is how we're going to do it. Generally, go from left to right on the periodic table. Except for hydrogen. Hydrogen always comes after carbon. Anyways, continuing on, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 carbons. We have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens. We have 1, 2 nitrogens and 1, 2 oxygens. Cool, so that should be the formula for melatonin. Now, if you're off by 1 hydrogen or 2 hydrogens or, you know, something like that, don't worry, I'm not going to mark it off. If you're off by like 6, then it's like, okay, yeah, you've messed up something pretty bad. But yeah, try your best to get within the range. Also, these are multiple choice for these questions, so again, don't sweat it too much. You'll be able to figure it out. Anyways, let's just double check our work. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Cool. Okay, so that is the number of carbons, and then hydrogens. Okay, we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Cool. Okay, that looks pretty good. All right, so keep going. This also I really wanted for you guys to do, because especially this is what we call a fatty acid, right? Which you guys have seen in biology. You've seen this thing, right? Oftentimes it's also shown like this, where it's like, oh, and then you kind of have a lipid head. But yeah, now you know what the zigzag is. It's just carbon and hydrogens, right? And so that's kind of cool to know. And so next year you'll see it a little bit differently. But anyways, continuing on, we're almost done. 2 more. Which bond is more polar? Y, CO, or NO? Remember, that's just going to be the electronegativity differences. And so C and O has what type of difference? That's what? 0.89, right, for CO. Versus for NO, it's going to be 0.4. And so which one is more polar? Well, it's always going to be the one that has the bigger electronegativity difference, right? And so it's going to be CO, bigger EN difference. Okay, so that's how you do those type of problems. Just take the electronegativity difference, and whichever one has the bigger one is going to be more polar. And then lastly, we get to number 10, which is asking you which will have the higher boiling point and why. And my hint here is think about IMFs, or molecular stickiness. The more sticky the molecules are to one another, the more energy will be needed to cause the substance to boil, / the higher the boiling point therefore will be. And so really this is a question of IMFs. It's asking you, hey, which one has the stronger IMF? Remember that of the IMFs, first place is ion-ion. Second place is hydrogen bonds. Third place is dipole-dipole. Fourth place is induced / LDF. Now, note that actually technically everyone has induced / LDF, but it's the one for nonpolars. Nonpolar covalent is the only one it has, and that's why we associated with it. So if you take a look at my answer key for your 5.8 problems, you'll see that it says, yeah, also it has induced / LDF for all of them, and because that's true, but because all of them have it, it doesn't really make a difference. But anyways, all that to say, let's take a look here and say what type of IMF each of them have. So H2O is going to be, it looks like this. And there is that big electronegativity difference, as we know. And so there's pulling, and then there's overall net pull, and so it is polar. But not only is it polar, remember my phone joke today, right? If H is bonded to F, O, or N, it's going to be hydrogen bonds, hydrogen bonding. And so therefore, here we have hydrogen bonding. It's a specific type of polar. It's going to be the hydrogen bonding IMF. And yeah, so this actually has pretty strong molecular stickiness. H2O is very sticky to each other. Versus for C3H8, looks like this. And so it is going to have, or this is just a hydrocarbon. And so it is going to be nonpolar, right? And so therefore, if it's nonpolar, it only has induced / LDF. And so therefore, which one is going to have the higher melting point? Which one is going to need more energy to separate out the molecules? It's going to be H2O, right? H2O, because it has hydrogen bond IMFs, which are stronger than the induced dipole / LDF IMFs of C3H8. Cool, so that's a good thorough answer for that one. And so kind of similar thing for B, try to figure it out. And yeah, so hopefully that helps you guys. If you need any additional help, feel free to come by my tutorial tomorrow. I'll also be here extra early for you guys on Friday. So come in the morning. But yeah, otherwise you guys got it. Celebrate your learning. You guys have learned a lot. Actually, this is very high level chemistry, to be honest with you guys. This is, yeah, definitely much further than I ever get with my at-level chem classes, and also just in general much more than normal sophomore year chemistry courses at different schools are. And so great job, you guys are doing great, you guys are killing it. If it is hard, please don't feel bad. It's chemistry, it's hard, especially AS chemistry. But you guys are doing great, keep up the good work. Let me know if you need any help, and yeah, I'll see you guys soon.